Hello, and welcome to the TI Precision Lab module discussing challenges with 3-wire RTD systems. Measuring a 3-wire RTD introduces additional challenges depending on the type of measurement system used. This presentation covers how 3-wire RTD measurement system behavior changes when using 1 versus 2 IDACs, as well as the differences in performance between a low side versus a high side reference resistor. The effects of IDAC mismatch error are also considered. As discussed in a previous Precision Labs module, 3-wire RTD systems can use 1 IDAC or 2 IDACs for automatic lead cancellation. Each of these methods has advantages and disadvantages. On the left is a 3-wire RTD system that uses a single IDAC to bias the RTD. This implementation has the benefit of eliminating IDAC mismatch errors because only 1 IDAC is used. The challenge with this method is that it requires 2 measurements, which doubles the measurement time compared to the 2 IDAC method. On the right is a 3-wire RTD system that uses 2 IDACs for automatic lead cancellation. The challenge with this method is that if IDAC 1 and IDAC 2 are not perfectly matched, an additional error is introduced into the system. As stated in the top right, both RTD measurement systems shown here use a low side reference resistor to generate the ratiometric reference voltage, though a high side RF is possible. The high side RF requires additional analysis for a 3-wire RTD using 2 IDACs, which is considered later in this presentation. The analysis is the same for a low side versus high side RF when only 1 IDAC is used. Let's analyze each circuit in more detail, beginning with the 3-wire RTD circuit using 1 IDAC. A 3-wire RTD using 1 IDAC requires 2 measurements to implement automatic lead cancellation. The circuit for measurement 1 is biased using IDAC 1 as shown. The IDAC current follows the path highlighted in red through R lead 1, then RTD, then R lead 3, and finally through RF to ground. Measurement 1 is taken between inputs AN0 and AN1, which is highlighted in blue. Using Kirchhoff's voltage law, the measured voltage, VN1, is the difference between the voltage seen at AN0 and AN1. VN1 is given as V lead 1 plus V RTD, which is the sum of the voltages across R lead 1 and the RTD respectively. The configuration for measurement 2 is shown in the middle of this slide. Note that the IDAC biasing is the same and therefore no changes need to be made to the circuit configuration. Instead, we just need to change the input path to measure the voltage between AN1 and AN2. The measurement path is shown in blue. As before, the measured voltage, VN2, is the difference between the voltage seen at AN1 and AN2. VN2 is given as V lead 3, which is just the voltage across R lead 3. Now, let's calculate the resulting ADC code. As a reminder, the equations for VN1 and VN2 are shown in the top right, while both measurement circuits are shown on the left. The equation for the reference voltage, Vref, is shown as the product of IDAC 1 and Rref. Note that this equation is the same for both measurement circuits, but it is only highlighted on the circuit for measurement 2. Next, we need the equation for the ADC code. A simplified equation is shown on the right, which is just the input voltage divided by Vref. For now, we can ignore the different constants required to generate the actual ADC code because this just scales the final result. We can then apply the values for VN1, VN2, and Vref to the ADC code equation as shown. The R lead 1 and R lead 3 terms cancel out such that the final ADC code equation for a 3-wire RTD using 1 IDAC is R RTD divided by Rref. This outcome assumes that R lead 1 equals R lead 3, which is a fair assumption due to the way that RTDs are constructed. Slight variances can occur, but generally not to the level that would cause a noticeable error in the ADC output. A subsequent Precision Lab series on error sources briefly introduces the concept of lead resistance mismatch. However, unless otherwise noted, we will assume all lead resistances are equal throughout the rest of this series. It should also be noted that the final ADC code equation does not depend on the absolute value of the IDAC, and is therefore ratiometric. Finally, this same analysis applies to the systems using either a low-side or high-side RREF. The main benefit of this configuration compared to using two IDACs is higher accuracy because there is no IDAC mismatch error. The challenge with this configuration is increased measurement time, though this is typically an acceptable trade-off for higher accuracy systems. Now, let's look at a 3-wire RTD configuration that uses two IDACs. Shown here is a 3-wire RTD measurement system that uses two IDACs and a low-side RREF. While both current sources are used simultaneously in this circuit, let's analyze the bias path for each separately, starting with IDAC 1. The red current path from IDAC 1 flows from the top IDAC pin through our lead 1, then our RTD, then our lead 3, then through our RREF, and finally to ground. Note that this is the same path used by the current source in an RTD system using one IDAC. At the same time, the blue current from IDAC 2 is output on the bottom IDAC pin. This current passes through our lead 2 and meets IDAC 1 at the bottom of our RTD. Similar to IDAC 1, the IDAC 2 current then flows through our lead 3, then our RREF, and finally to ground. Now, there are two currents flowing through the bottom half of the RTD measurement system. For the sake of simplicity, the portion of the circuit where the combined currents of the IDACs flow is represented by the purple line. Next, let's calculate the measured voltage, Vin, which is the difference between A and P and A and N. We can again use Kirchhoff's voltage law to calculate that Vin is V lead 1 plus VRTD minus V lead 2. Each of these terms can then be expressed as a product of the IDAC current and the respective resistance. The final expression for Vin is shown as the sum of our RTD and our lead 1 multiplied by IDAC 1 minus the product of IDAC 2 and our lead 2. Now, let's calculate the resulting ADC code. First, we need to keep the equation for Vin as shown on the top right. On the left is the 3-wire RTD circuit using two IDACs and a low-side RREF from the previous slide. We also need the equation for the reference voltage, Vref, which is shown as IDAC 1 plus IDAC 2 multiplied by RREF. Next, we need the equation for the ADC code. A simplified equation is shown here, which is just the input voltage, Vin, divided by Vref. Similar to the case where only one IDAC is used, we can ignore the different constants required to generate the actual ADC code because this just scales the final result. We can then apply the values for Vin and Vref to the ADC code equation as shown. Now, let's assume that IDAC 1 is equal to IDAC 2, which allows us to simplify the ADC code equation in terms of just the circuit resistances. Lastly, let's also assume that our lead 1 is equal to our lead 2. This assumption yields the final ADC code equation for a 3-wire RTD system using two IDACs, which is our RTD divided by 2 times RREF. In other words, the ADC code does not depend on the absolute value of the biasing source, and is therefore ratiometric. Note that this result is specific to a 3-wire RTD measurement system that uses two IDACs and a low-side RREF. The analysis is different when using a high-side RREF, which is discussed in more detail later in this presentation. Before moving on to analyzing a circuit with a high-side RREF, however, let's first consider the two assumptions made on this slide. While we have previously justified assuming the lead resistances are equal, we have not validated the assumption that the IDAC output currents are equal. Therefore, let's delve into the specifications for the IDACs integrated into the ADC to understand how practical this assumption is. Shown here are the specifications for the IDACs that are integrated into the ADS124SO8. This 24-bit low-power Delta Sigma ADC was used in previous Precision Labs modules because it integrates many features that simplify RTD measurements. One such feature is dual-matched IDACs. As shown, the ADC datasheet includes a variety of IDAC specifications. For example, the compliance voltage specifications ensure that both IDACs can maintain constant current, in this case to within 0.1% deviation. This parameter was discussed in more detail in a previous Precision Labs module. The next set of parameters specify the absolute performance of each IDAC. For example, the accuracy specification says that the 100 microamp output current setting can have a maximum variation of plus or minus 5%. In other words, the actual output current can be anywhere from 95 microamps to 105 microamps. Note that there are different specifications for different output current ranges. Similarly, each IDAC is subject to temperature drift. That same 100 microamp output current setting has a maximum temperature drift of 100 ppm per degree Celsius. If the ADC temperature increases by 80 degrees Celsius, the IDAC error due to the temperature drift is almost 1%, and this error can be in addition to the accuracy error. The main takeaway from these specifications is that the absolute IDAC output current is not very accurate. However, this is by design. Since the IDACs are intended to be used in a ratiometric measurement, their absolute performance is not important. Instead, the matching specifications are the most critical for 3-wire RTD measurement systems using 2 IDACs. Highlighted here in yellow, the ADS124S08 datasheet includes both current mismatch and temperature drift matching specifications between the 2 IDACs. Note that these specifications are much better compared to the absolute accuracy of each IDAC. For example, the maximum current mismatch between the IDACs when the output current is 100 microamps is 0.8%, or 900 nanoamps. This is better than 6 times the performance of each IDAC. Similarly, the maximum temperature drift matching is significantly better between the IDACs at only 25 ppm per degree C for the 100 microamp output current. Assuming the ADC temperature increases by 80 degrees Celsius, the IDAC matching error due to the temperature drift is only 0.2%. This is a 5 times performance improvement compared to the absolute temperature drift of each IDAC. Now that the IDAC matching specifications are more clear, let's consider how IDAC matching affects the performance of a 3-wire 2 IDAC RTD measurement system using a low-side reference resistor. To begin the analysis, let's keep the current mismatch error parameters from the previous page. These are shown in the top right. On the left is the RTD measurement system we are analyzing. Then, we need to recall the ADC code equation for the system shown on the left. In this case, we will continue to assume that RLEAD1 is equal to RLEAD2 as discussed earlier in this presentation and replace those terms with RLEAD. However, we will not assume that IDAC1 equals IDAC2, which means we will not be able to further simplify the equation shown here. Instead, let's modify the equation by deriving a relationship between the specified IDAC mismatch error, EIM, and each IDAC magnitude. This relationship is highlighted in yellow. Note that the choice of dividing IDAC1 by IDAC2 is arbitrary, such that the mismatch could also be defined as IDAC2 divided by IDAC1. This changes some of the equations, but the resulting calculations are identical. Also note that by definition, EIM must be less than 1 because IDAC1 and IDAC2 are both positive non-zero values. If IDAC1 is greater than IDAC2, then EIM will always be some negative value. If IDAC2 is greater than IDAC1, EIM will always be a number greater than 0 and less than 1. As an example of what this equation represents in a real system, if the current magnitude for IDAC1 is 500 microamps and IDAC2 is 503 microamps, then the calculated mismatch error between them is 0.6%. Finally, we can rearrange the mismatch equation and solve for IDAC1 as shown on the bottom right. This new equation can be substituted into the ADC code equation, which is discussed on the next slide. As a reminder, let's keep the error equation and the equation for IDAC1 from the previous slide. These are shown on the left. We also need the ADC code equation, which is shown on the top right. Next, let's substitute the IDAC1 equation on the left into the second equation on the right. With the ADC code equation only in terms of IDAC2, we can cancel out the IDAC2 term in the numerator and the denominator of this equation, as well as distribute the terms on the top. This yields the third equation on the right. Then, we can simplify the equation further by removing our lead and combining like terms. Finally, rearranging terms results in an equation that separates the error related to the RTD and the error related to the lead resistance, which is highlighted in yellow. This form of the equation helps us answer the question, how much ADC error does IDAC mismatch contribute to the system? To calculate the ADC error that results from the IDAC mismatch error, let's start with the general form of the error equation shown on the top right. We take the difference between the ideal and mismatched ADC codes and divide this result by the ideal code to calculate the ADC error in percent. Applying the system-specific expressions results in the second equation on the right. Similar to the IDAC2 term on the previous slide, we can divide out RF because it appears in all terms. Let's now multiply the top and bottom by 2 divided by RRTD to get rid of the denominator and further simplify the equation. This is a valid operation because RRTD can never be 0, which means 2 divided by RRTD will always be a non-zero value. Next, we can set the constant value of 1 in this equation equal to 2 minus EIM divided by 2 minus EIM. This is a valid operation because 2 minus EIM must always be a non-zero value. Further simplification and factoring out the common variable results in the final form of the error equation, which is highlighted in yellow. Note that the algebra on this slide and the preceding one are shown for completeness, but the equation highlighted in yellow is the most important takeaway from this analysis. Let's now review how this analysis changes when using a 3-wire RTD, 2 IDACs, and a high-side RREF. Then we will be able to quantitatively compare the error equations for a low-side and high-side RREF. Shown on the left is a 3-wire RTD measurement system that uses 2 IDACs and a high-side RREF. As before, let's see how the current flows from each IDAC through the circuit and to ground. The current from IDAC 1 is highlighted in red, which follows the same path as the 3-wire RTD using 1 or 2 IDACs and a low-side RREF. Comparatively, the current from IDAC 2 in blue passes through our lead 2 and meets IDAC 1 at the middle lead of the RTD. At this point, both currents combine and are represented by the purple line. The combined current flows through our lead 3 and our bias to ground. Note that this is different from the low-side RREF circuit where both currents flowed through RREF. Next, let's calculate the measured voltage, Vin, which is the difference between ANP and ANN. We can use Kirchhoff's voltage law to calculate that Vin is V lead 1 plus VRTD minus V lead 2. Each of these terms can then be expressed as a product of the IDAC current and the respective resistance. The final expression for Vin is shown as the sum of RRTD and R lead 1 multiplied by IDAC 1 minus the product of IDAC 2 and R lead 2. Coincidentally, this is the same result for the 3-wire RTD system using 2 IDACs and a low-side RREF. Now, let's calculate the resulting ADC code. As before, let's keep the equation for Vin, which is shown on the top right. On the left is the 3-wire RTD circuit using 2 IDACs and a high-side RREF from the previous slide. We also need the equation for the reference voltage, Vref, which is shown as IDAC 1 multiplied by RREF. Unlike the low-side RREF configuration, the factor of 2 in the denominator is missing because only one IDAC flows through RREF. Next, we need the equation for the ADC code. A simplified equation is given as Vin divided by Vref. Similar to the previous cases discussed in this presentation, we can ignore the different constants required to generate the actual ADC code since this just scales the final result. We can then apply the values for Vn and Vref to the ADC code equation as shown. Now, let's assume that IDAC1 equals IDAC2, which allows us to simplify the ADC code equation in terms of just the circuit resistances. Lastly, let's also assume that R lead 1 is equal to R lead 2. This assumption yields the final ADC code equation for a 3-wire RTD using 2 IDACs and a high side RREF, which is R RTD divided by RREF. In other words, the ADC code does not depend on the absolute value of the biasing source and is therefore ratiometric. Note that this result is specific to a 3-wire RTD measurement system that uses 2 IDACs and a high side RREF. Just as we did for the low side configuration, let's now analyze what happens if IDAC1 does not equal IDAC2. Shown on the left are the error terms we derived during the analysis of the 3-wire 2 IDAC circuit using a low side RREF. The general form of the ADC code equation for a 3-wire RTD measurement system using 2 IDACs and a high side RREF is shown on the right. First, let's substitute the IDAC1 equation on the left into the second equation on the right. With the ADC code equation only in terms of IDAC2, we can cancel out the IDAC2 term in the numerator and the denominator of this equation, as well as distribute the terms on the top. This yields the third equation on the right. One further simplification allows the 1 minus E1 term to be cancelled out from the R RTD divided by R RREF term. Finally, rearranging terms results in an equation that separates the R RTD and R lead terms. This form of the equation helps us answer the question, how much ADC error does IDAC mismatch contribute to the system? To calculate the IDAC mismatch error, let's start with the general form of the error equation shown on the top right. We take the difference between the ideal and mismatched ADC codes and divide this result by the ideal code to calculate the ADC error in percent. Applying the system-specific expressions results in the second equation on the right. Similar to the IDAC2 term on the previous slide, we can divide out RREF because it appears in all terms. Dividing each term by RRTD simplifies the expression even further. This is a valid operation because RRTD can never be 0. Lastly, the RRTD terms cancel out, resulting in the final form of the equation, which is highlighted in yellow. Note that the algebra on this slide and the preceding one are shown for completeness, but the equation highlighted in yellow is the most important takeaway from this analysis. Now that we have the ADC error equation for a 3-wire RTD system using 2 IDACs and a high side RREF, we can compare it to the ADC error equation for a low side RREF. To begin the comparison, we'll need the error equations for both systems. These equations are given in the first row of the table, where the low side RREF is in blue and the high side RREF is in the brown column. Next, let's apply some conditions to each equation to better understand how they differ. First, assume that the IDAC mismatch error is small, or less than 2%. This is a conservative assumption because IDAC mismatch error is typically much smaller for ADCs with integrated matched current sources. For example, the ADS124SO8 has a typical error of 0.15%. As a result of this assumption, we could simplify the equations for both RREF configurations. These new equations are shown in the second row of the table. Then, let's assume that R RTD is approximately equal to R lead. This is not a practical assumption because RTD lead resistance is usually very small compared to the minimum RTD resistance. However, this can be considered a worst-case scenario. As shown in the third row, the low side RREF error is 1.5 times higher compared to the high side RREF error, even under these extreme conditions. Finally, consider the more common case where the RTD resistance is much larger compared to the lead resistance, which is shown in the fourth row. Under these conditions, the error for a system using a low side RREF is approximately equal to 1/2 the IDAC mismatch error. This outcome occurs because the R lead divided by R RTD term in the equation in the second row of the table approaches 0 as R RTD increases. Comparatively, the error for a system using a high side RF is approximately 0. Note that these different outcomes result exclusively from the fact that both IDAC currents flow through the RF in a low side configuration, whereas only one IDAC current flows through RF in a high side configuration. Let's now graphically verify these conclusions. First, let's keep the equations for both the low side and high side RF configurations, which are shown on the top of this slide. Next, let's select multiple IDAC mismatch errors and plot each equation across a range of RTD resistances. For this example, let's choose a range of 20 ohms to 380 ohms because this is the measurement range of a PT100 RTD. In all three cases, our lead is chosen to be 1 ohm. In each plot, the low side RF error is shown in blue, while the high side RF error is shown in brown. The blue plots confirm the approximation for the low side RF. In each case, the error across the RTD resistance range is approximately 1/2 of the IDAC mismatch error. Comparatively, the brown plots show that the error using the high side RF is 0 in all cases, confirming this approximation as well. Ultimately, whenever possible, choose a high side RF for a 3-wire RTD measurement system using 2 IDACs. If this is not possible, or the resulting error is still too large, performing IDAC chop is one way to help reduce the effect of IDAC mismatch errors. IDAC chopping is a technique that involves taking one measurement, swapping each IDAC position, taking another measurement, and then averaging the results. This should ideally eliminate IDAC mismatch errors. Let's step through how this process works. On the left is the circuit for measurement 1. In this measurement circuit, both currents flow from their respective IDACs through the RTD, through RF, and then to ground. As shown, the purple line represents the portion of the circuit where both IDAC currents are flowing. The equation for the first ADC output code is shown on the bottom left. Each term in the equation is color-coded with the appropriate IDAC current. Finally, note that the output from IDAC 1 in red biases the top lead of the RTD, while the output from IDAC 2 in blue biases the middle lead of the RTD. Let's move on to the second measurement circuit, which is shown on the right. To implement IDAC chop, it is necessary to swap the location of the IDACs. Many precision ADCs can perform this function without external components, such that the physical circuit is the same as in measurement 1. For example, the ADS1262 includes an IDAC chop mode that automatically switches the IDACs between measurements and averages the results. Other ADCs, including the ADS124SO8, have flexible input multiplexers that allow the user to manually perform this switching by just changing register bits. If the ADC does not have these integrated features, it can be necessary to add additional switching components to implement IDAC chop. For measurement 2, the output from IDAC 1 in red now biases the middle lead of the RTD, while the output from IDAC 2 in blue biases the top lead of the RTD. This yields a slightly different equation for the second ADC output code, which is shown on the bottom right. However, both equations have the same denominator because the combined IDAC currents flow through RF in both cases. Next, we need to take these two measurements and average them together to determine the final chopped result. Let's start with the general form of the averaged ADC code, which is just the sum of each code divided by 2. Applying the system-specific expressions results in the second equation on the right. The color coding from the previous slide has been maintained. Next, combine all of the IDAC 1 and IDAC 2 terms together. The third equation on the right shows how both IDAC 1 and IDAC 2 are multiplied by the same term in the numerator. The fourth equation is further simplified by factoring out this term. Assuming R lead 1 equals R lead 2 yields the fifth equation. Finally, the IDAC terms in both the numerator and the denominator cancel, resulting in the ideal IDAC ADC output code equation for a 3-wire RTD measurement system using 2 IDACs and a low side RF. For a system using a high-side RF, the IDAC chop procedure is exactly the same, but the final ADC output code equation is RRTD divided by RREF. One challenge with this method is that performing IDAC chop requires two measurements to generate a single ADC output, which increases the system cycle time and can add analog settling delays due to the IDAC switching. If increased cycle time is acceptable, it is recommended to just use a single IDAC and avoid IDAC chopping altogether. The measurement time will be the same, and there will be no need to be concerned about IDAC mismatch errors or settling time due to swapping the IDAC currents. Moreover, the mathematical operations required to implement IDAC chop are more complicated compared to the simple subtraction that calculates the final ADC output code for the one IDAC configuration. This RTD measurement configuration was described earlier in this presentation. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content. Question 1. True or false? Measuring 3-wire RTDs using one IDAC generally has lower error compared to using two IDACs because the two IDAC method introduces IDAC mismatch errors. The correct answer is A. True. Question 2. When measuring 3-wire RTDs using two IDACs, which configuration has the lowest error? The correct answer is B. The high-side reference configuration. Question 3. True or false? Measuring 3-wire RTDs using two IDACs is faster compared to using one IDAC because two IDAC method only requires one measurement. The correct answer is A. True. Question 4. What is IDAC chop used for? The correct answer is C. IDAC chop is used to remove IDAC mismatch in 3-wire, two IDAC systems by taking one measurement, then swapping the position of the IDACs, taking another measurement, and finally averaging the results. Question 5. What is the disadvantage of IDAC chop? The correct answer is A. Two measurements are required, which increases measurement time. That's all for today's video. Thanks for watching.